All right, so all of our vocabulary comes from section 1.2. And I'm going to say, I'm just going to call it basic vocab. So that's what we've been doing on our sheet. So what I want to do is kind of get some different ideas from folks about what they wrote on their graphic organizers, and I want to make sure that we all have our proper names for our proper name / notation. So if you want to volunteer your answers, that's good. In order to encourage everyone, I have a little deck of cards here that has everyone's name on it, that I can draw names at random to get some input. So let me get that ready. I just had to shuffle them a little bit. All right, so let's talk about our basic vocabulary. I want to give you a little bit of history first before we get into our vocabulary. The geometry that we're studying is called Euclidean geometry. And that's because in around 300 BCE, a gentleman by the name of Euclid wrote a series of books called the Elements, which one of the most famous sets of books in all of math. A pretty famous set of books in the world as well. He was the first person. He didn't discover all of the geometry, but he was the first person to put it together as starting with some ideas and then building on those ideas using logic. So he was one of the first people to do that. And he based geometry on a small amount of things like point, line, and plane, and some ideas about points, lines, and planes, and then used logic to build up what we know about geometry. So that's why it's important. And part of what we do in this class is we don't necessarily follow the path of trying to reinvent geometry, but we learn about logic and applying logic to what we're doing. So geometry is a little different than what you do in algebra, where you learn, okay, for this kind of problem you do these series of steps and you have the problem solved. In geometry it's more along the lines of, well, you know this and you know that. Now we need to use logic to figure out other stuff. All right, so our first term was a point. So that was on your graphic organizer. And I said it's an undefined term, so it doesn't have a technical definition. But what are some important facts or characteristics about points that we might want to include as facts or characteristics? Who could help us out with fact or characteristic? Yeah. A location. A point is we think of a point as a location. So if you don't have on your facts and characteristics part of your graphic organizer, you might want to put that on there. How big is a point? Yeah. No size. So that's a pretty important fact or characteristic. How do we, when we write it, how do we know we're talking about a point? What do we write on our paper? What's that?
We use capitalized letters.
Capitalize. So one step before, just if we wanted to say on a graph, how would we show a point? A dot. We write it as a dot. And now, what Isabeau said, so to name them, we use capital letters. So for example, we would say point A. That would be how we would name point A. So in your book, on a quiz or a test, if you see this, a dot and A, it's talking about the point named A. So that's how we name a point. So make sure that you have how we properly name a point written down on your graphic organizer. All right, a line was our next undefined term. No technical definition. What's an important factor characteristic about a line? Yeah.
It has no thickness.
No thickness. Yeah, go ahead.
Because both directions.
Both two directions infinitely. Yes.
I was going to say it's represented by a straight path.
It's a straight path. I like that. That's a good one to have. It's a straight path. So we're not, when we're talking about a line, we're not talking about a curvy thing. It's straight. No thickness, two directions infinitely, straight path. All right, so next one. How do we, well, we know we talked about it in the opener. We name by 2 points on the line. So a line could have a bunch of different names depending on the points that are shown on the line. So we would say, I'll do the same drawing as our opener. If this is a line and it has points A and B on it, we would write line AB. And that's exactly how we would read that, line AB. And we would know that that means the line through AB. If we had more points, if we had C, D, E, and F, we could use any 2 points that are on that line. So since it goes two directions infinitely, how many points are on a line? An infinite number of points. So that's this is one of the reasons these are undefined terms. It's an idea that we can think of it, we can imagine it, but it's not, they're not, points and lines and planes are not real things. They're kind of ideal things. All right, so that would be good for a line. What's an everyday way that we think of a line? What would be an example of something that would be like a line? Yeah.
Roads.
Yeah, a long straight road. They're not quite infinite, but that's how we think of a line. A long straight railroad track. The path that an airplane flies if it's going across the country. So something like that. Next one, plane. Who can help us out with a fact or characteristic about a plane? Yeah, Tyler.
Has no thickness.
No thickness, just like a line. All right, do you have one?
Represented by a flat surface.
It's a flat surface. So the line was a straight path. A plane is a flat surface. Where does a plane go? Yeah? Without ends.
Points.
In how many directions?
Everywhere.
Yes, very nice. It extends infinitely in all directions. So if I took this table up here and extended it out in all directions, that would be kind of how we think of a plane. Infinite in all directions. So if we're showing a plane, if we wanted to represent a plane on a picture, how do we do that? Anybody have that? We wrote a parallelogram, kind of a little box shape. So that's how we represent a plane. Even though it has boundaries, we imagine that it extends in all directions. Did anybody get how planes are named? This one I want you to pay particular attention to because students find it tricky. We name it using 3 points. and the points can't be on the same line. So if I have this, here's my plane, and if we have points A, B, and C, these aren't all three on the same line, we would write the little parallelogram. That's plane A, B, C. So in your book, that's what it would say. This is plane ABC, and they'd be talking about that thing. And I'm going to say, or script capital letter. So I'm going to put a capital R here in the corner of the plane. So this script R is not naming a point. So we could call this plane R. I would say you can never go wrong by naming it with 3 points that aren't on the same line. Make sure if you're naming it with one letter that it's a script letter and the script letter is in the corner, because we don't want to use a letter that's naming a point. So that's how we name a plane. I'll usually write this, and it's easier not to make a mistake if you just do this. All right, so those are our 3 undefined terms. The next 2 are pretty easy. Collinear. Who can help us out with what collinear means? Some of you can read it off your graphic organizer. Yeah.
Points on the same line.
Points on the same line. That's all collinear means. So if we have a line that's supposed to be straight, all these points, we would call those collinear points. They're all on the same line. How about coplanar? Yeah?
There are points and lines that are all on the same plane.
Points or lines or and lines all on the same plane. So I'm just going to say points / lines on the same plane. So this, if you didn't have a picture for collinear, that could be a picture, a way of drawing collinear. Coplanar, we were just talking about a bunch of things that are on the same plane. There's some points that are on the same plane. There's a line that's coplanar with those points, etc. How about a segment? Now a segment, because we make it, these next things, we make them up from points, lines, and planes. So they do have a technical definition. So, can someone help me out with a technical definition of a line segment? Let me call on someone. Make sure they're here. Did you come up with a definition, Carolina? From the book? No? Alex, did you come up with a definition for a segment?
Part of the line.
Part of a line. That's nice. I want to add one piece to that. Did you want to add?
I was just wondering if I could go to the bathroom.
Yes. Mm-hmm.
It has this point of line with two endpoints.
Two endpoints. Nice. So if we drew a picture, we have our endpoints A and B. So a segment is a piece of a line. We chop the ends off so it doesn't go forever anymore, and we get a piece of a line. So these are our endpoints, A and B, pretty clear. And I said on the board we name it. Named with the endpoints. So we would call this segment AB. You can just draw the segment over the top without arrows. If it helps you remember, put the little endpoints on there. So you remember we're talking about a segment and not a line. It doesn't go forever. What would be an everyday thing that we could think of as a segment? A piece of a line. How about a pencil? Kind of like a segment. A ruler, right? Something like that would be an everyday way of thinking of a segment. All right, the next one, ray. Did you come up with a technical definition for array, Connor?
It's a line
Oh, we got two Connors. Go ahead.
It's a line that consists of like one endpoint, it's an arrow.
Right. We have a part of a line with one endpoint. And it extends infinitely in one direction. I kind of think of rays as half of a line. We cut one half off, it goes one way but not the other way. So, and Connor said it looks like an arrow. Like that. And I'm going to say that ray goes through point B. This is the end point. And we name them with the endpoints and one other point. So it goes through point B. So I would call this ray AB. And we draw a ray over the top. If we do it in the opposite order, I could do it this way. But we want to make sure the ray goes the right direction. So we want to make sure that A is the end point. Either one of those would work for the ray. What's a way we could think of a ray? Light, yeah. How about this? There's a ray coming out of the end of my flashlight. All right, our last one. Last vocabulary word, angle. We got a really nice technical definition in our last class. Anybody give me a nice definition of an angle? What do you think?
It's formed by two rays with the same endpoint.
Two rays with the same endpoint. Perfect. So we'd have something like this. to call this point B. That ray goes through point C. What do we call that endpoint? The vertex, yes. This part in here, oh, and one other thing, what do we call the rays as part of the angle? Did anybody get that? The rays are the sides. So we call the rays the sides of the angles. In here is the interior, and out here is the exterior. So when you'll hear a description of something and it'll say point F is on the interior of the angle. So that means it's somewhere in here. Now angles, naming angles students often find tricky. We name them with 3 points. The vertex has to be in the middle. So we use a little angle symbol. Angle, B, A, C. This is the vertex. So we always put the vertex in the middle because that tells us kind of which way the angle goes. Or, if it's not confusing, if there's not multiple angles with the same vertex, we can use just the vertex. So we could call this angle A. There aren't any other angles with point A as the vertex, so we could call that angle A. And I'm going to put a number in here, the number 3. That's not how many degrees the angle is. There's not a degree symbol there. Or we can use a number. So that could be angle BAC, angle A, angle 3. We could also call it angle CAB as long as the vertex is in the middle. So 3 different ways that we can name an angle. And because, I just want to point this out, because the sides of the angles are rays, angles go on forever. We usually think of parts of angles. We make angles with segments. But an angle by itself goes on forever. All right, so that should be the set of information that is on your graphic organizer, your vocabulary. That's the key vocabulary we'll need. And we'll be talking about points, lines, planes, rays, angles, that kind of thing, all the way through May. Collinear, coplanar. All right, the next part, not for your graphic organizer. This is a little bit of new information. We want to talk a little bit about intersections. So, what would you guess we mean when we say two figures, two geometric things intersect? Just based on the word itself. Yeah. They come together. Intersect means to come together or meet. So we have two lines that are intersecting. They're meeting. They're coming together somehow. Our book with the way our book is a little fancier, they say when figures intersect, they have points in common. That just means they meet. What would you guess that we're going to call the place where they come together, or the place where they meet? So two things are coming together, two roads are coming together. What do we call that place? The intersection. Intersection is where they meet. So one of the first things that we're going to be interested in, now that we know a little bit about points, lines, planes, rays, angles, segments, is intersections. What happens when they come together? What happens when they meet? So we're going to have what we call postulates about these things. We'll have postulates throughout the year. A postulate is something that we accept as true without proof. So we need to start somewhere with geometry. The somewhere is with our undefined terms and then with our postulates. So we have some postulates today about intersections. And I think we can all figure out the postulates just by talking about them. So our first postulate. Two lines intersect. So let's think about two lines. Two infinitely thin, infinitely long things. They're going to intersect. They're going to meet. What are we going to guess that intersection is? What kind of thing would the intersection be? They're infinitely thin and they meet somewhere. Yeah? A point. Very nice. Two lines intersect in a point. I'm going to say in exactly one point. So that's our first postulate about intersections. Two lines intersect in exactly one point. So if I draw on your graph, remember in Algebra 1, you would solve systems of equations, and you would find the point, the x and the y, where those lines intersect. Exactly one point. All right. Our next postulate about intersections. Two planes. All right, so think about these two infinite surfaces, and they're going to meet somehow. Now remember that these are infinite, so my folders, even though my folders aren't infinite, we're imagining them as infinite, and they're going to meet. So they're going to touch somewhere. What are we going to guess that intersection is? Any idea? Are you stretching, or do you have any? You are raising your hand?
Does it make 2 points?
Well, it's going. There's definitely going to be 2 points, but remember these are infinite. So if I intersect these, so this one continues infinitely that way. This one continues infinitely that way. So that place where they meet, it's infinitely thin, but it's going to keep going infinitely. So it's going to be a line. Definitely has 2 points on it. The intersection of two planes is a line. So the way we could imagine it is this wall and the front wall meeting in this corner. The corner right where exactly where they touch, that corner, if it extended infinitely, it would be a line that went through the ceiling and through the floor. So two planes intersect in a line. Now I'm going to talk about 2 points. So let me draw a couple points. Well, I'll draw them here. Through 2 points is, so I have 2 points here. What could I draw? What kind of figure could I draw through those 2 points? We could connect it with a segment. What if we extended the ends of the segment? What would that be? A line. Could we draw a, if I drew a line through these 2 things, through these 2 points, like so, and remember our points are infinitely thin, could I draw another line through there that was different? That those points are infinitely thin. So there's nowhere to move up or down or sideways or anything. Could I draw another line?
No, because it would be skew, right?
Right? So we're going to say through 2 points is exactly one line. There's no way we can draw a different line through those 2 points because they're infinitely thin. We don't have anywhere to move, go a little bit this way or a little bit that way. They're infinitely thin. All right, our next one. And I think this is this the last one? No. One more after this. Through 3 points, not all on a line. So I'm going to draw, here are 3 points that aren't on the same line. What kind of geometric thing that we've talked about would contain all 3 of those points? Yeah? An angle, so a triangle maybe, because yeah, well, an angle could contain all 3, so that is true. Think for this postulate we're thinking a little bigger. What could the angle be in? A plane. Through 3 points not all on the same line is one plane. So these 3 points would all be on one plane. And we can't draw a different plane through those 3 points, just like the line, because the points are infinitely small. So there's no way we could angle another plane and fit it through those 3 points. So there's exactly one plane. This is, I think of this one as, this is why they make tripods with 3 legs instead of 4. Because those 3 legs, no matter how they're situated, they're always going to go flat onto the ground. That doesn't mean the tripod's not going to lean, but we can always get those 3 legs to sit flat without wobbling on the ground. If we make 4 legs, then you know how sometimes your table wobbles or your chair wobbles? Then they all aren't necessarily on the same plane. And finally, our last postulate about intersections. If 2 points are in a plane, or then the line, we know that 2 points make a line. Then the line through them is, so let me draw a picture here. Here's a plane. Here are 2 points that are on the plane. And I'm going to draw a line through those 2 points. Where does that line have to be? In the plane, exactly. So that line is going to be in the plane also. Because if those points are infinitely thin, there's no way to angle it and get the line to go out of the plane. So those are our intersection postulates. And this is what we're going to start building on when we start actually doing geometry on Friday and moving forward. All right, questions on our postulates? Okay, I have some questions for all of you. Why are geometric figures different than real-world objects? Yeah.
I
believe there's like never-ending possibilities for the shape to turn into.
Okay, so we said that all the lines are infinite, right?
Yes.
The planes are infinite. Are real world objects infinite? We said the top of my table is like a plane, sort of. But is the top of my table infinite? No. Is it perfectly thin? No. So that infinite piece with the geometric figures is what makes it different from real world objects. Why can we not name a plane with just one point? Why couldn't I draw up here on my board this point A and say, okay, the name for the plane that my whiteboard is plane A? Why is that one point not enough? Yeah? It has infinite. Yeah, there are a bunch of planes or lines or things that could go through point A, right? If I made a plane out of this folder, doesn't that plane go through point A? Isn't it touching point A? Yeah? So if I said plane A, we wouldn't know if I'm talking about this one or this one. Here's another plane that goes through point A. Different from all those other two. If we called one of them plane A, how would we know which one we're talking about? So that's why we need more than one point to name a plane. Why can't we name a plane with 2 points? Why couldn't I say, all right, one's not enough. I'm going to put point B up here and say the whiteboard is plane AB. There, now I've fixed that. This one, the one that's vertical, that one wouldn't go through A and B. Is there another plane that I could make go through plane or point AB? How about this horizontal folder? Doesn't that go through point A and B also? How about this diagonal folder? Or this other diagonal folder? So 2 points doesn't give us enough information to know we're only talking about one plane. All right. Why, last question. Why are the orders of the letters important when we name angles? Yeah, Isabel?
Because the one in the middle is always going to be the vertex.
We need to know where the vertex is. Which one's the vertex? If we just put the letters willy-nilly, we wouldn't know which one the vertex is. So we wouldn't know exactly how our angle goes. So we need to make sure we know where the vertex is. All right. Our homework is a worksheet, so I want